A mass M of 3.2 kilograms hangs motionless from the ceiling from two identical massless springs with spring constant of 507 newtons per meter. Each spring makes an angle of 60 degrees with respect to the horizontal as shown. Okay? How much is each spring stretched from its equilibrium position? Okay. So first thing we think about is force balance. Since there is no net force, since there's no acceleration, we have no net force. So the sum of all forces equals 0. So we draw the forces here. We have force due to gravity. I'll call this force due to spring 1, force due to spring 2. 2. And so we can write this. We can just set them equal to each other. We can say that, some are positive, some are negative. But I'm going to look at it, kind of skip a couple steps here. So we have force gravity equals force spring 1 in the y direction plus force spring 2 in the y direction. And since the two springs are identical, we can just call this 2 force spring 1 y. We can use spring 2 as well, but I prefer 1. And so now, to find this y direction, so here, force spring, force due to the spring, just in general, will be negative k delta x. I'm just going to call this k delta x though, so it'll be a k constant times the amount it's displaced from equilibrium, which is what we're looking for. And then we're going to want to use just the sine component here. So this is going to be 2k delta x sine of theta. And the idea here is we only want the y component, so if this is theta, then this value right there, that'll be the sine of theta times the hypotenuse. Hypotenuse being force of the spring. Okay, so now we got our formula. So force gravity, we're going to call this mass times gravity equals 2k delta x. That's the displacement from equilibrium, sine theta. We're looking for delta x. Click, clack. We have delta x equals mass times gravity over 2k sine of theta, which now is bum bum bum. Bing 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 bing. Okay, so we got mass, which is 3.2. So we have 3.2 times 9.81 gravity times 2. That's just going to be 2. And then K, which is like 702, 507. Way off. 507 times the sine of 60, which is like 0.86. Bum, bum, bum. Right there. Okay. Should I give us an answer? I think that'll give us an answer. So then we use our calculator. Pull up the calculator. Clear. Check our mode real quick. Click, click, clack. Degrees. Make sure in degrees, not radians. So we'll do 3.2 times 9.81 divided by quantity, 2 times 507, which is just 1014. And then we'll divide again by quantity, sine of 60. Click, clack. And we get an answer of 0.0357. Whoa, too much. 0.357. And this will be measured in meters. And we have an answer of, right here, D, 0.036. Not too bad. Okay, now the second part is, if the angles were both changed to 45 degrees, the springs would, I believe they would stretch more, because the idea here is the more vertical the springs are, the more their force is concentrated upward. Therefore, it would be more in line with the gravity, and therefore we have to, the sine of theta would be a bigger proportion of the total force. Therefore, you need less force. But for something, if you have a couple minutes, if you have a couple seconds, the easiest way to do this would be, since we already have our equation up here, I'll call this dx of 60. This would be the delta x of if it's 40. Go back, we have 3.2, 9.81. You probably can leave that one off. 2 times 507, which is 1014. but I'm just going to write it this way. Sine of 45. Whoop, whoop. And since we already had our equation right up there, let's just throw in the calculator again, see what happens. So we have 3.2 times 9.81, that's 31.92, 0.392, I already have it up there, divided by quantity 2 times 507. I probably could take some more shortcuts, but I haven't yet. Yep, that should be sent. And then now we're going to divide by quantity sine of 45. Click, click. And we get 0.438. 0.0438. So this number is bigger than that number, therefore stretched more? Well, that seems weird. Ah, yes, it's true. Okay, so at first I thought when they said the angle changed to 45, I thought I was moving it this way. Totally wrong. It's actually moving the springs this way, so they are less in line with forced gravity. See, probably a good thing I checked that. So the springs will actually have to stretch more. So A, the springs will have to stretch more than before. Okay? Back up, kind of review what we did here. So we did a free body diagram. We know there was no motion, therefore the net force, all the forces added together, would be 0. Another way to look at that would be, we could say that forces up would equal forces down, since we're specifically focused with up and down here. Therefore, we set the force times gravity equal to force times the springs. We can only use a portion of the spring force because it's a vector and it's at an angle. And we know that the force due to the spring is some sort of spring constant times its deviation from the equilibrium position. Put all that data together, shake it up a bit, do some algebra, and we get an answer. So not too bad. Hope that helped. I will see you next time.